Today we're going to talk about partial fractions. So let's recall a couple things from previous lessons. First, if we take the integral of 2t plus 1 over t squared plus t, the first thing we would probably think about is, can we do a U-substitution? And the answer is yes, we can do a U-substitution here. So if u is t squared plus t, then du equals 2t plus 1 dt. That perfectly aligns with what the numerator is. And so if that's the case, we can make a U-substitution, 1 over u du, because if I replace that with u, and then I can replace dt with du over 2t plus 1, and then that cancels out the 2t plus 1s. So I have 1 over u du. I integrate that. I get the natural log of u plus c, which is the natural log of t squared plus t plus c. So that's something that we've learned before. We also learned that if it doesn't exactly align, we have u equals t squared plus t, du equals 2t plus 1 dt. We can rewrite the numerator of this problem as 2t plus 1. That's not what it says. And notice that this is the same thing as 2t plus 1 plus 2. So we could have the integral of 2t plus 1 over t squared plus t dt plus the integral of 2 over t squared plus t dt. And then we could kind of do a similar thing. We have a U-substitution over here. So this ends up being the natural log of t squared plus t, just this part on the left. And then the part on the right, what we would have to do is complete the square. We learned how to do that in a previous chapter. I'm not going to spend a whole lot of time doing it right now because completing the square is actually not that fun, since this number has an odd value. But we could complete the square and use an arctangent type of thing for that part. So this is plus something else. So notice there were two things that we could do here. But what if I tell you that on the problem on the right, instead of splitting it the way we did it in the past, what if I tell you that we can use what's called the method of partial fractions? And so if I rewrite this as the integral of 2t plus 3 over t times t plus 1, so notice I factored the denominator. What I can do here is I can rewrite this. So if I take a little sidebar and I say that I have 2t plus 3 over t times t plus 1. Something you learned in honors pre-calculus is that you can rewrite this equation as a over t plus b over t plus 1. And then all we have to do is find out what a and b are. So if I do that, I can basically get a common denominator. And then once I do that, basically multiply through by the common denominator, I end up getting 2t plus 3 on the left. And then when I look at the right, if I multiply through by the common denominator, I'll get a times t plus 1 and b times t. So notice the common denominator would be t times t plus 1. I can basically wipe that denominator out. And now what I'd want to do is rewrite this in such a way where I can make it look like 2t plus 3. So if I have 2t plus 3 on the left, at plus bt plus a on the right, that's the same thing as a plus b t plus a. So ultimately what I have here is I have a plus b must equal 2 and a must equal 3. So if a equals 3, then b has to equal -1, because 3 plus -1 equals 2, and that was what it had to be. So if I, and again, you can rewind or something if you need to see that again. So A was 3 and B was -1. So if I notice that, what I can do is I can take this integral and I can rewrite the integral like this. And now this problem is relatively straightforward. So now I just have to integrate this, and I get the natural log of, 3 times the natural log of t minus the natural log of t plus 1 plus c. Now that problem we just did, we would actually end up getting the exact same answer if we completed the square and did all that other stuff. But this problem actually doesn't work very well with an arctangent because it ends up being something that can be factored into linear factors in the denominator. But that's beside the point. So this would be the answer to that problem. So then how do I know when I need to do something like this and get partial fractions? So this is a method called partial fraction decomposition. So I took something that had something that was factorable in the denominator, and I turned it into multiple factors, multiple different fractions that had those factors. And that's exactly how you know when to do it. You know to use partial fractions if you have something that doesn't have an easy use sub, like on the left up here, but you can factor the denominator. And so this is an easily factorable denominator, and so that is something that we wanted to do. If you look back at the previous lessons where we did some splitting it into two things, where we had a U sub and an arctangent and stuff like that, like a forcing the one situation, we didn't have anything that was factorable in the denominator. So if we have something that's factorable in the denominator, we want to use partial fractions. Now, if we have something like this, some numerator divided by a bunch of stuff. So let's say we end up factoring the denominator. How do I split this up into partial fractions? So notice I have a linear factor, x minus r. If I have a linear factor, I always put just some constant in the numerator over whatever that is, so x minus r in the denominator. If I have a quadratic factor, I'm going to put a linear term in the numerator. So in this case, bx plus c over x squared minus t. Now I have this linear factor that is repeated. So anytime I have a repeated linear factor, I have to do as many linear factors as necessary in order to get up to the power that I have. So this has a power of 3. So I'm going to do d over x minus w plus e over x minus w squared plus f over x minus w cubed. So notice they're all linear factors. The x itself is not being squared, so I just have to put a constant in the numerator up there. And then finally, I have this x squared minus p, the quantity squared. So if I have a repeated quadratic factor, I'm going to have gx plus h over x squared minus p. And then I have one more term that I have to write, ix plus j over x squared minus p squared. And I have to do that because there's a repeated factor, and I have to do it as many times as the power. So that's just an example of how to do that. And then what you're going to do is you're going to take this numerator and set it equal to what happens when you multiply all of this by the common denominator. Now, obviously, in this problem, that would be a nightmare, but we're going to do it in problems that are a lot simpler, so then we don't really have to worry about it nearly as much. So here's a first example. The integral of 5 over x squared minus 5x plus 6. So the first thing I'm going to do is notice that this is something that is factorable in the denominator. So I'm going to do the integral of 5 over x minus 3, x minus 2 dx. So since that's factorable, what I'm going to want to do is rewrite this with partial fractions. So notice that 5 over x minus 3 times x minus 2 can be rewritten as a over x minus 3 plus b over x minus 2. So now that I have that, now I'm going to multiply through by the common denominator. So I have 5 equals a times x minus 2 plus b times x minus 3. And then I just have to do a little bit of simplifying here. So I have ax plus bx. So if I simplify that, I'll get a plus bx. And then I have negative 2a minus 3b over on the other side. So that equals 5. Notice that 5 is the same thing as 0x plus 5. So that's just something to keep in mind. So I have a system of equations that I can now solve. So I have a plus b must equal 0. And I have 5 must equal negative 2a minus 3b. So since a plus b equals 0, that means a equals negative b. And now I can make a substitution. So if a equals negative b, that means I have 2b minus 3b equals 5. So negative b, I should probably scroll the page up a little bit. Negative b equals 5. So b equals negative 5, which means a equals 5. So now that I have that, I can now rewrite all of this as this integral. So if I have the integral of this dx, I have dx. A was 5, so I have 5 over x minus 3. And then I have negative 5 over x minus 2. And so now I integrate this. So I have 5 times the natural log of x minus 3 minus 5 natural log of x minus 2 plus c. So that is problem 2. I'll move all that over a little bit. Oh no, I'm not going to move that. That might ruin some things. Okay, so if we look at the next problem, I have 6x plus 7 over x plus 2 squared. This is a repeated linear factor. So since this is a repeated linear factor, I'm going to rewrite this as a over x plus 2 plus b over x plus 2 squared. And so now it's basically just a matter of multiplying through by the common denominator. So the common denominator is x plus 2 squared. So this is a times x plus 2 plus b, and that equals 6x plus 7 after I multiply through by the common denominator. So I get ax plus 2a plus b equals 6x plus 7. So notice that a has to be 6 because that's the only thing that has an x. And since that's true, if a is 6, 2 times 6 plus b must equal 7. So that means b equals negative 5. So let's integrate. So I have the integral of 6 over x plus 2 dx plus the integral of negative 5 over x plus 2 squared dx. So when I integrate this, I get 6 times the natural log of the absolute value of x plus 2 minus, well, the integral of this is not going to be a natural log. So what I have to notice is that x plus 2 in the denominator squared. I might have to make a u sub until I kind of figure out what's going on. So if u equals x plus 2, then du equals dx. And so that means this is basically, I'm not going to have to make any sort of multiplications there. So I can basically just treat this like it's negative 5 over a variable squared. And so if I have a variable squared, the integral of that is actually just negative. So I'll do this kind of in a thought bubble over here. If I have the integral of 1 over u squared, that ends up being negative 1 over u. So negative 5 over x plus 2 squared, the integral of that is going to be the opposite. So that's plus 5 over x plus 2. So that is the answer for that second thing. To the back side, I'll go through these a little bit quicker. The first thing I'm going to do in the first one is factor the denominator. So we have x squared minus 6x plus 2. The denominator, we can factor out a GCF of x. So we have x squared plus 2x plus 1. And then this bottom part, x squared plus 2x plus 1, factors into x plus 1, the quantity squared. So we have x, which is a linear factor, and x plus 1 squared, which is a repeated linear factor. So x squared minus 6x plus 2 over that is the same thing as a over x plus b over x plus 1 plus c over x plus 1 squared. And so now our objective is to take this and multiply through by the common denominator. So x squared minus 6x plus 2 is equal to a times x plus 1 squared, which I'm just going to write as x squared plus 2x plus 1. B is missing an x and an x plus 1 from its denominator, so it's b times x plus 1. And then c is just missing an x. So the x squared terms need to end up equaling 1. So 1 ends up equaling a, because there's an ax squared, and there's also a bx squared, because if I take x times x plus 1, that's the same thing as x squared plus x. So I have a bx squared term. So I have 1 equals a plus b. The x terms, I have 2a plus b plus c equals negative 6, because that's what the x terms will end up equaling. And then a equals 2 is the last thing, because there's only one term that has a constant for anything, and that, or there's only one variable that has a constant for anything, and that's a. So I'll take a equals 2. I can substitute that into this equation over here, which means b equals negative 1. And then when I take a equals 2 and b equals negative 1, I get 4 minus 1 plus c equals negative 6, which means c equals negative 9. So when I take all of that, I get 2, 1, and negative 9. And I can replace a, b, and c with those things. So I have 2, negative 1, and negative 9. And so now I just have to integrate this. So this is equal to 2 times the natural log of x minus the natural log of x plus 1. And then this one is plus 9 over x plus 1. And we learned that in the previous side, because if we have negative 9, when we integrate the squared term in the denominator, it changes the sign. So it's going to end up being plus 9 over x plus 1. And then that's plus c. So that's that one. If I look at the problem over on the right, this is the same thing as the integral from 1 to 2 of x plus 1 over x times x squared plus 1. And so notice I'm doing partial fractions. The first thing I should probably do is see if there's a u sub that might work. But in both of these problems, there was no u sub that would work. So in this problem, I have a linear factor and a quadratic factor, neither of which is repeated. So I can just rewrite this as a over x plus bx plus c over x squared plus 1. And so the integral of that dx, and this is actually the integral from 1 to 2. Excuse me. So now I have to multiply through. So I have a times x squared plus 1 plus x times bx plus c. So I'm just multiplying through by the common denominator, and that equals the numerator, which is x plus 1. So I have ax squared and bx squared. So I'm going to have an ax squared and a bx squared, and that's going to end up equaling 0, because if I have x plus 1, that means there's a 0x squared that's kind of in the front, and so ax squared plus bx squared has to equal 0x squared. So a plus b equals 0, which means a equals negative b. Then I have cx, that's our only term that actually has just an x component. That equals 1x, so that means c equals 1. And then I also have a equals 1, because a times 1 is 1a, and there's no other terms that don't have any variables with it. So a equals 1, and since a equals negative b, that means b equals negative 1. So I have a equals 1, b equals negative 1, and c equals 1. So I can take all of that, and I'm going to erase this stuff so I have enough room to write some stuff down. So a is 1, b is negative 1, and c is 1. So I put a 1, negative 1, and 1 up here, and now I integrate this stuff. So the integral of 1 over x is the natural log of the absolute value of x, and I'm going to take the integral of this and turn it into something that's a little bit easier to integrate, so we'll separate the numerator. So instead of writing negative x plus 1 over x squared plus 1, we will write this as minus x over x squared plus 1 plus 1 over x squared plus 1. And when we do that, if we look at the first one that I'm going to circle in green, that can be done with a u sub. So x squared plus 1 is u, du, oops, not ud, du equals 2x dx. And so I can replace negative x over x squared plus 1 with 1 over 2u, and then that's kind of like a mini du in there. So when I integrate that, that's going to be minus the natural log of the absolute value of u with a 1/2 in front, because this 2 can kind of move to the outside since it's a constant. So 1/2 natural log of u, remember u was x squared plus 1. And then we should know the back part already. The integral of 1 over x squared plus 1 is arctangent of x. And then we have a plus c. So that is the problem on the right. Oh my, there was a it's a definite integral. My bad. So plus arctan of x, and then we have to evaluate this from 1 to 2. So let's try that again. So when I evaluate this and I sub in 2, I get the natural log of 2 minus 1/2 times the natural log of 5 plus arctan of 2 minus, when I sub in 1, I get the natural log of 1, which is 0, plus 1/2 natural log of 2, and then minus arctangent of 1. And so I can simplify that more, but in the interest of time, I'm not going to do that. It's like 3/2 natural log of 2 minus 1/2 natural log of 5 plus arctangent of 2, and then arctangent of 1 we can simplify to be pi over 4 or whatever it is. To summarize partial fractions, basically you want to do it when there's no easy u sub or integration by parts, and it's basically something where you have easy or maybe not so easy factoring in the denominator. So when you do that, we end up doing what we showed on the front, where you can rewrite something that has things in factored form into multiple different fractions with plus or minus signs in between them. And then after that, that makes the integrating easier because it's easier to integrate when you have multiple fractions instead of one giant fraction. And then if you can't factor it, then you have to go back to the things that we might have learned earlier, like completing the square in order to turn it into an arctangent problem, or something along those lines.